welcome to another video on the laws of sines and cosines. Today we are going to be looking at situations where we could get multiple triangles from one given set of information. So this arises when we are looking at the side-side angle case. So let's say that we know that angle A is 40 degrees, side B is 10 units, and side A is also given. So notice I drew side C to be way longer than it needed to be. But let's say that we knew that side A was only going to be 1 unit long. Well, if I go to draw the triangle here, well, there's no way, if side A is 1 unit, that I'm going to be able to make a triangle, because I'm not going to be able to reach from angle C up here all the way down to side C if A is only 1 unit. I'm not going to be able to make a triangle. So what I want to think about is well, if side A is given in this scenario, what is sort of the smallest that side A could be to complete a triangle? So if I was to draw inside A from vertex C here, the shortest distance from this point to side C would be if I made side A perpendicular to side C. That would be the shortest distance from vertex C up here all the way down to side C. What would that make side A? Well, I could solve for that really quickly because this is a right triangle. So the sine of 40 would equal side A over 10. So 10 sine 40 would be side A. So let's just compute that really quick. So in this scenario, if A was given to be 6.428, we could draw exactly one triangle. We would have this right triangle here. If A was less than 6.428, we wouldn't be able to draw any triangles. So let me start to categorize these scenarios down here. So if side A was given to be less than 10 sine of 40 degrees, we would end up with no triangles, no possible triangles. If A is given to be exactly 10 sine 40, so if A is about 6.428, we would get exactly one triangle that we could form here. Now let's just think about the geometry of this situation here. If A was given to be really large, 30 units, I mean, what would our triangle look like? Well, we wouldn't be able to draw the triangle from this vertex like to the side down here if A was really long, because the side just wouldn't fit down over here, because the length of side B is only 10. So if side A was given to be really, really large, like larger than 10, we wouldn't be able to draw an obtuse triangle here. We would have to draw side A way out here like this. So basically, if A is given to be bigger than 10, anything bigger than 10, we're also going to get one triangle. And our triangle would look like the triangle that I've drawn here. So if angle B was way down here, let's say side A was given to be something really big, like 17 units, we would wind up with this really, really big, potentially obtuse triangle. So basically, with the side-side angle case, you can think of the situations that would form one triangle sort of in the following ways. So now the interesting scenario is going to arise if side A is given and it's bigger than 10 sine 40, bigger than 6.428, but less than 10, because then we would be able to draw sort of angle in right here, like so, and draw another triangle potentially over there. So that's sort of the key here. When the angle is going to be bigger than 10 sine 40, but less than 10, we can create two triangles. So let's sort of explore this idea further. So, okay, so we've got, let's make A 9 in this case. So there's sort of two pictures I could draw. I could have A being 9, so I could sneak her and make that 9 units. And there's angle B. So that's one possible that's one possibility for what my triangle could look like. Or I could swing side A over here like this, make that 9 units, There's angle B. So see how there's two potential pictures that I could draw here, because 9 is less than 10, but bigger than 10 sine 40. So now we could use sort of the law of sines and solve for all of our various sides and angles and whatnot. So let's start to do that. So let's say over here I'm going to just do the law of sines. So I got the sine of 40 over 9 equals the sine of b over 10. So if I multiply both sides by 10 and then take the sine inverse of both sides, that's going to give me angle B, which is 45.578 degrees. So now looking at the two pictures that I've drawn, that's probably this angle down here. Because it looks like in this picture up here, this angle B is going to be very obtuse. From this picture down here, it looks like C has the potential to be obtuse. So now if I continued on using law of sines, I could solve this triangle down here, and I would end up getting that C is 94.422. All the angles have to add up to 180 degrees. Then I could do the law of sines to solve for side C, 13.960 units. I could fill in my chart over here, and it looks like I did my picture reasonably to scale. These numbers look great. So now what's going on here is that, remember, the sine inverse function has a restricted domain and range. When you do the sine inverse here of this angle, it's only going to give back an acute angle because the restricted range on the sine inverse function is negative 90 degrees to positive 90 degrees. If angle B here, like this angle B, is obtuse, but the sine inverse function is never going to return an obtuse angle, it's going to return an acute angle that has the same sine value as that obtuse angle. So like what's going on here is that if I think of the unit circle, sort of angle B, so there's two possible triangles. So one possibility for angle B is that it could be like 45 degrees. That would be like here on the unit circle. Another possibility for angle B is that it's going to be obtuse. It's going to be over here. It's going to be the angle that has the exact same sine value as 45.578 degrees, meaning it's going to have the same sort of height on the unit circle, meaning it's going to be the supplement of angle B. Because remember, if this right here is 45.578 degrees, then this reference angle would also be 45.578 degrees to make sure that these 2 points have the same height on the unit circle. So this obtuse angle B, the sine inverse function, returns only this angle in quadrant 1 because of the restricted range of the sine inverse function. Remember, the sine inverse function is only going to return angles between negative 90 degrees and positive 90 degrees. So then we sort of have to think about, like, okay, well, what is that other possible angle? And then luckily it's pretty easy to find. It's just going to be 180 minus 45.578, which is 134.422 degrees. So that is that angle B right there. And then I could quickly solve for my new angle C. It'll be 5.578 degrees. And then do a quick law of sines computation to find side C. And that's going to be 1.361 units. So these cases are pretty tricky because you really have to think about, when you're using the sine inverse function, you know, it's always going to return an acute angle, so you've got to be thinking about, is the obtuse angle that has that same sine value a possibility for making that second triangle. Another course of action would be that you could set this up using the law of cosines. So, you know, we could have taken this given starting information. Hey, now why did I pick that version of the law of cosines? Well, because I know angle A. So I picked that version of the law of cosines. Now watch what happens once I substitute in my given information. I get 9 squared equals 10 squared plus c squared, I don't know side c, minus 2 times b times c times the cosine of 40 degrees. So if I subtracted 9 squared from both sides, and I'm just going to rearrange my terms here, I get c squared minus, this is minus 20 cosine of 40 times c plus 10 squared minus 9 squared. So I'm left with a quadratic equation in c. This is 1c squared. This negative 20 cosine of 40, that's just the coefficient on c. And then 10 squared minus 9 squared, that's just a constant. So I have a quadratic equation that I can solve for c. So I've got a bunch of different options there. I could do the quadratic formula, or I could use my calculator. So if you do the quadratic formula, just be really, really careful. So we know what the answers are going to be because we just solved this problem previously. C is going to be 1.361 or 13.960 units. So try to solve this quadratic equation using the quadratic formula. Be really careful with just how you type everything in the calculator. See if you can get those two answers. Or we could use sort of the graphing feature of the calculator here. So we could set up our equation, c squared minus 20 cosine of 40c plus 10 squared minus 9 squared. Notice I'm saying c squared. I mean, the calculator doesn't have a c, it's just coming in as x. That's totally fine. I had to play with the window a little bit. So remember, like, side c that I'm solving for here, it's a side of a triangle, so I made x min, or c min, I guess I'm thinking of it that way, is 0. Then I had to think about, like, well, what's probably the maximum that side C is going to be? I just threw like an 18 there. I thought that side C probably wasn't going to be any bigger than 18, but it's kind of a guess. You might have to play with this window a little bit. Made the scale 2. I think that'd be fine. The y min, y max, I'm just sort of, again, might have to play around with those a little bit, just judging by how big the coefficients are in your equation. Kept the y scale at 1. Didn't really matter. First seeing a great graph, and the x-res doesn't matter. I think I had it at 1. So in checking out the graph, looks good. I see that this quadratic equation has 2 positive real roots, which means that there's 2 positive real numbers that we're going to get for c, and that means that there's 2 triangles present. If one of these roots was negative, that wouldn't make sense in the context of this problem because side c is the length of a side of a triangle. So if I had 1 positive root and 1 negative root, well, then I would only have 1 potential triangle. If there were no roots at all, that would correspond to that case where no real roots. That would correspond to the case where there's no possible triangle. So you see I found this 0 here. So C was 1.361. And then I've got the chart filled in, because once I know that, then I can carry on my way doing the law of sines, the law of cosines, whichever I prefer, to figure out the rest of my sides here, or my angles, rather. Just be careful that if you're using the law of sines, so if you know all 3 of these sides, the only angle that could be obtuse here would be angle B, because it's opposite the biggest side. So if you had all this information and you were using the law of sines, make sure that you would solve for this angle C first. Because remember, if you were using sine inverse, I wouldn't return the correct angle for angle B since it's obtuse. So if you had this set up here, I'd use law of sines and solve for angle C, and then go on my merry way. If you're using law of cosines, you could solve this in any order, in any way that you please, because the cosine inverse function returns angles between 0 and 180 degrees. So the restricted range of the cosine inverse function isn't much of a problem. Then over here, found this root. This corresponds to the side where C is 13.960. Right down here. And then again, if we're using the law of sines, just don't solve for angle C first.